Alright, now we'll start learning about how to do standard addition. First, I will describe a scenario, and then we'll learn how to solve this problem. An unknown sample of iron 2 plus gave an absorbance of 0.372 in an AAS analysis. Then 75.0 milliliters of this unknown solution was spiked with 15.0 milliliters of solution that contained 80.0 ppm iron 2 plus. Let's pause there and address some terms. To spike a solution means to add something to that solution. Also notice that this 15.0 milliliter spike contains a known concentration of our analyte. So this is our standard addition right here that we're going to add directly to the unknown. So let's resume the problem. 10.0 milliliters of water was then added to bring the mixture to 100 milliliters, and its absorbance was measured again as 0.600. So notice the absorbance value has increased between pre-spiking and after spiking. That makes sense because we've just added this iron here to the iron that was in our unknown solution. And now the goal is to find out what the original concentration of iron 2 plus was in the unknown when it was by itself. Now let's toss that visual in the corner for reference and learn how to do the problem. We'll start by writing the key equation. And let's build this up. We are interested in learning the concentration of the analyte in the unknown, which we will use the following symbol to denote: concentration X. And this concentration, when measured, generates a signal. In the word problem, we were told that absorbance signal was 0.372. For now, though, we'll just use the symbol I, and I'll give it a subscript X to denote that we're referring to the intensity of just the unknown. Then, we measured the intensity again after some standard was spiked into that unknown sample. And that intensity had grown from 0.372 to 0.600, which makes sense because the total concentration of analyte had been increased, because we now had the unknown concentration plus the known standard concentration that we spiked in. So this here represents the analyte concentration total in spiked mixture. The total Fe2+. And the reason that I have arranged the symbols as I have is because we're about to make two ratios happen and set an equality. Now here's what this equality is stating. If our concentration of the analyte were to, say, double once we've added that standard in, then we would expect the intensity of the signal to double as well. And that makes complete sense. This is just another way of saying that the relationship between concentration and measured signal is linear. Triple the concentration of the analyte by adding in that spike, well, we should triple the intensity of the signal. Now, one very important consideration to take into account is that whatever these initial concentrations of our standard and unknown are, well, they're about to both be diluted because we are mixing these two together to give a larger volume of solution. So the contribution of analyte from the standard will be lower than 80 ppm in the larger volume. Whatever this unknown concentration is, it's also going to be smaller in this larger volume solution. However, while each individual concentration may be diluted, as the two combine, we'll have a larger concentration of analyte total than ever before. So the intensity in turn will be larger than when the unknown is by itself. So with all that in mind, let's add some subscripts to this equation. The X concentration in the numerator is the initial concentration before anything has happened, but the X term in the denominator is the final concentration after the mixture is made. And we will also add an F subscript to that standard concentration. Now, while this might seem more complicated, we know how to deal with it, because again, these are just diluted concentrations. And what's the formula for dealing with diluted concentrations? M1V1 equals M2V2. So what we're going to do is just plug in that formula as needed. So let's start plugging numbers into this equation based on what was given here and in the prior word problem. Hopefully things will become more clear as I go through this. So I'm going to start by rewriting the equation, but this time I'll put in numbers when I can. So top left, concentration of the unknown before anything happens. This is what we want, so we definitely don't know that. The whole purpose of this experiment is to figure that number out. On the bottom though, we can't write XF, because then we're going to have two different unknowns. The initial unknown concentration that we want, and the final unknown concentration after the volume that it's swimming in has increased. We need to express this unknown number in terms of this unknown number. How do we do that? Well, we're going to write initial unknown concentration times 75.0 divided by 100.0. How did I come up with that? All I did was I used the dilution formula, and I'll draw this off to the side. We know M1V1 equals M2V2. What I'm doing is I'm changing the symbols. Instead of using M1, I'm going to call this initial concentration of X, which is what we see in these equations. Instead of saying M2, we'll label that final concentration of X, like in the equation. V1 would just be what is the volume of just the unknown by itself, Vx, and V2 we'll label as Vf. What is the final volume of the mixture? So same exact algebra, just new symbols. And we know what the volume of the original unknown was. It's 75.0, and we know the final volume, it's 100.0. So from here I just do some algebraic rearrangement and plugging in numbers as I can. We have on the left side x initial times Vx, which we have identified as 75.0 milliliters, I won't bother writing the unit, divided by Vf, which we have identified as 100.0, and on the right side we're left with just final concentration of the unknown. And so I'm just plugging in that expression over here to give me this. And then I'm going to use the same logic to deal with that SF term. I'm going to take that initial concentration of standard, and this time I do know the number because it's a standard, right? 80.0 multiplied by its initial volume, 15.0, divide by the final volume of the mixture, 100.0. And that is the left side of our equation. Now the right side is much easier to set up. The intensity of the unknown by itself, it's not on this slide, but we can grab it from the previous word problem. It was 0.372. And the intensity of the signal when we measured the final mixture was 0.600. And from here it's just an algebra problem. I mean, it's a rather long algebra problem, but the hard part is over. The chemistry is over, which was just figuring out how this setup works. I'll solve it in a few steps. Let's simplify that left side. And let's say that's x initial, again, this is what we want, divided by 0.750, x initial, plus, and then that 80 times 15 divided by 100 winds up being 12.0. And then the right side is still 0.372 over 0.600. I'll do another intermediate algebra step, which is just cross multiplication to make it a bit simpler. On the left side, we will have 0.600 times xi, 0.600 times xi, and on the right side, we will have 0.279 times xi, 0.279 times xi plus 4.46 little 4 plus 4.46 little 4. And again, I got this by just cross-multiplying. From here, the algebra is simple, so I'll just solve it and tell you that the initial concentration of the unknown is equal to 13.9. 13.9. Now, we haven't been tracking our units as we've been doing the math, but we can figure out what the units are based on the units that we were initially given. Our concentrations were in terms of ppm, and so the final answer should be ppm. So 13.9 ppm. And that's the problem. It looks like a lot, but notice it was just 3 steps. 1. Set up the equation. 2. Express the final concentrations as initial concentrations, which is ultimately just the dilution formula. And 3. Plug in the numbers and solve. Now, while this is one way to do the standard addition analysis, it ultimately suffers from the fact that it's based on a one comparison measurement. You measure the unknown, and then you compare it to a single addition of standard. We've already discussed why we would rather use a graph based on multiple measurements rather than just relying on a single measurement. Those arguments still hold true. So in the next video, we will discuss how to do a graphical procedure using multiple standard additions.